this video exists. You hear my voice. You see the picture changing on the screen. You realize the meaning of what I'm saying. In short, you perceive it. In this case, the existence of this video is not questioned by the main philosophical concepts that consider being reality from different points of view. Suddenly, you are bored, distracted, or stop watching altogether. Does this video continue to exist? As science has progressed, scientists have inevitably asked such questions, generating numerous examples, the most famous of which are the falling tree paradox and Einstein's question about the moon. The paradox boils down to the following: is the sound of a tree falling in a forest audible if no one is around? It sounds pretty obvious. Yes, there will be a sound. Or, if you appreciate the content, please show your support by liking, subscribing to the channel, leaving a comment, and sharing this video with your circle. Your engagement greatly aids the algorithm. On April 5, 1884, a similar question was published in one of the most respected popular science magazines, Scientific American, and the article gave the following answer. Sound is an airborne vibration transmitted to our senses through the auricular system, and recognized as such only in our nerve centers. The fall of a tree or any other mechanical action will produce a vibration of the air. But if there are no ears to hear, there will be no sound. At first glance, it would seem that the problem here is only in the definition of the term sound. But in fact, the issue at hand is much deeper and involves basic questions of philosophy and physics. Do you really believe that the moon exists? Only when you look at it? Einstein asked his opponents on questions of quantum theory, giving us another special case of one of the most important questions of mankind. What's out there where we're not? Let's go in order. I'm not going to make it mysterious. And I will say at once, there is no unambiguous answer to such fundamental questions. I can only try to cover this topic as interestingly as possible, share some thoughts, familiarize you with the main concepts that offer this or that explanation, and it is up to your discretion which of them to join or not to join at all, provided, of course, that free will exists. But now, it is not about that. In general, this question, as it was said earlier, has two sides, philosophical and physical. You probably know that in philosophy, ontology deals with questions of being. In fact, everything comes down to what is primary in our reality, material or spiritual. Different approaches to this question have formed two main trends in this section of philosophy: materialism and idealism. Materialism asserts the primacy of matter over consciousness. It exists independently of our perception, divides into different forms according to internal laws, and does not need anything but itself for its existence. Human consciousness is thus understood as a natural product of the evolution of the material world. At this point, as is often customary among scientists, the proponents of one idea again divide into two camps. Adherents of vulgar materialism treat consciousness as a kind of matter, and as if the brain secretes thought as well as the liver secretes bile. Their opponents, consistent materialists, see in it the properties arising at a certain stage of development of the material world due to the reflection of the fundamental ability of material bodies to reproduce by means of their own changes the features of bodies interacting with them. The existence of reflection is quite easy to be convinced of. These are, for example, footprints, your footprint in the snow, scratches on the phone screen, fossils. All this is the result of the impact of one body on another, and it stores information about this interaction. The property of reflection has a universal character, that is, it is inherent in all matter, and its highest level is consciousness. But this position did not suit everyone. Many philosophers of different epochs, such as Plato, Thomas Aquinas, Immanuel Kant, in contrast to materialists, put the spiritual component in the first place and became known as idealists, initially appearing in the works of the same ancient Greek thinkers. Idealism also divided into two currents. Objective idealists argued that the world was the result of the activity of an ideal primordial being existing objectively, independent of human consciousness. Be it God, an absolute idea, a flying macaroni monster, Azathoth, or Hegel's world mind. Subjective idealists such as George Berkeley, whose work, incidentally, gave rise to the paradox of the falling tree we are considering today, considered the consciousness of each person, that is the subject, to be the original of being. All objects of reality exist only in our consciousness and are created by it, they believed, while denying the objective nature of all reality. Moreover, over time, an extreme form of idealism, solipsism, was formed, which asserts the sole existence of the perceiving subject. That is, all reality is the result of the activity of a single consciousness. And, of course, that consciousness is a solipsist's consciousness. So while materialists survive in a shared reality, solipsists form their own. Of course, materialism and idealism are not the only currents regarding the primacy of matter or mind. These are maximally opposite points of view, between which there are, for example, such currents as dualism, monism, and pluralism. Here, in principle, is the whole basis. Materialism is closer to you. A tree makes a sound, and the moon is in the sky without us. Idealism, the sound, like the moon, doesn't exist without us. But what about the physical side of the question? At first glance, it might seem that physics would certainly be on the side of the materialists. Einstein himself asked his question rather ironically. After all, at that time, the two fundamental physical principles of locality and realism were not questioned. The principle of locality, or as it is also called, proximity, means that particles interact only by direct collision or by exchanging other particles whose speed cannot exceed the speed of light. This principle is perfectly illustrated by billiards. If we want to roll a ball into a hole, we cannot simply teleport it there. We have to first hit one of the other balls with the cue, which in its turn will roll the ball we need. And the speed of all this action is limited by the speed of light. I like to see such an impact, although the energy released would be so great that it wouldn't be possible to watch for long. The principle of realism assumes that all objects have objectively existing values of their parameters and characteristics for any possible measurements that can be made on these objects, and before these measurements are made. In other words, to use the billiards analogy again, we can measure the mass, smoothness, density, and volume of a ball fairly accurately. And all these parameters are relatively constant. They were so before the measurement and will remain so after it. Thanks to this property, having made certain measurements and calculations, we can predict with surprising accuracy how an object will behave if we have some impact on it. And we can guess, for example, by scratches on the ball, what impact has already been made. So, it turns out Einstein is right, and idealists just made up selfish theories. But here's where it gets interesting. In classical physics, everything is indeed governed by these principles. But the smaller the objects we consider, the less classically they behave. And when we get to the quantum level, the principles of objective realism suddenly turn out to be not so inviolable. Traditionally, any conversation about quantum mechanics begins with a mention of Schrödinger's cat and Young's two-slit experiment. It's almost a bit of a mauvaise, but if we will not conduct experiments with the cat and radiation, of course, the Young experiment is simpler. From the school course of physics, we know that light has the properties of a wave and a particle at the same time, but it wasn't always like that. From the time of Newton until the beginning of the 19th century, most scientists were inclined to the corpuscular theory. That is, light is a stream of particles. This theory prevailed until the landmark year of 1803, when Thomas Young performed his famous experiment, which we will repeat. Let's take a beam of light, in this case, a laser pointer, and let's direct its beam at an opaque sheet of foil with two parallel holes, behind which there is a projection screen, since light at that time was considered to be a particle. Then, in idea, two stripes should appear on the screen, one for each hole, transmitting light particles. But, as you can see, the result was different. In fact, by directing the light through these slits, a diffraction pattern was reflected on the screen. We clearly see that instead of two stripes are seen several lighted and several dark stripes, as if light hills and hollows, which is possible only if the light as a wave envelops the obstacle, and then these secondary waves interfere, that is, overlap each other, forming maxima, light spots, and minima, dark. And so, for almost 100 years, light is a wave. But in 1900, while trying to solve another quantum paradox, the so-called ultraviolet catastrophe, German physicist Max Planck suggested that light, like any other energy, propagates in finite portions. Moreover, not long after, another scientist discovered the photoelectric effect. This is when ultraviolet radiation knocks electrons out of the atoms of a metal plate, which is possible only if light consists of particles, photons. That scientist, by the way, was Albert Einstein. This is where things got really confusing. There is convincing evidence for both seemingly contradictory versions. And to set the record straight, the scientists went back to Young's experience. But this time, they made the light stream discrete, so dim that it was possible to register individual photons. Each photon at the approach through the slits left a single trace on the screen with a seemingly random location. But accumulating from photon to photon, these traces formed the very diffraction pattern. From this, it followed that the photon interferes with itself, passing through both slits. On the basis of this and other experiments in 1924, Louis de Broglie proposed the theory of corpuscular wave dualism. Light is both a wave and a particle. But here began something from the realm of fantasy. Scientists decided to observe which of the slits a photon flies through by placing a detector in front of each one. It's important to realize that observing subatomic particles is a complicated process. It's not the objects that we're observing, it's the light reflected from them. So if we were shining a laser in a vacuum, we wouldn't see the beam itself. There would be nothing to reflect it off of. Therefore, to observe a photon, they needed a photon detector, which involves certain difficulties. It's much easier to track an electron, for example. This particle already has a rest mass, and it can emit photons on its own, losing energy in the process. In 1937, Clinton Davison and George Thomson discovered electron diffraction. And in 1974, a two-slit experiment was conducted with electrons and detectors at the slits. The result, as they say, was astonishing. In the absence of detectors, the electron behaves as usual, passes through both slits, many stripes on the screen, and so on. But in their presence, an amazing thing happens. It is as if the electron recognizes that we are watching it and flies through only one slit, forming two stripes on the screen. It seems as if the presence of the observation affects the electron, and it goes from being a wave not localized in space to being a particle localized in a certain place. This phenomenon has been called wave function collapse, or decoherence. It's not even that surprising. It's frightening. But even that's not the end of the story. After all, if we put a detector at only one of the slits, for example, the first one, then an electron arriving through the second one would seem to be unaffected by the measurement. It will still somehow guess that it has been tracked by the detector at the other slit and will not show its diffraction pattern. Let's pause for a moment, because the following experience breaks our conceptions of reality altogether. But to understand its essence, we must familiarize ourselves with two key concepts of the quantum world: superposition and entanglement. For a visual explanation of superposition, all you need is a simple balloon and a candy bar. Let this candy be the position of the electrons in space. So, by putting it in the balloon and inflating it, we get a model of the electron in superposition. As long as we have not measured its state, it is as if smeared in space. It is in several places at once, which also helps it to pass through two slits at once. We can only assume its position with a certain probability, which is exactly what the wave function describes. Well, so we decide to pinpoint the position of the electron by measuring it with a needle. And as soon as we do that, the wave function, just like the balloon, collapses, and the electron from such a cloud of probabilities assumes a single position in space. That's clear. But what about entanglement? In complicated words, entanglement is a quantum mechanical phenomenon in which the quantum states of two or more objects become interconnected. Once again, let me give you an example. Let's take an ordinary pair of socks. From the looks of it, both nipples are identical. There are no differences as long as they are reasonably clean. Each of them can be both right and left. That is, like Schrodinger's cat, is in two states at once or in superposition. But here, you put the first sock on your left foot, and at the same moment, I repeat instantaneously, the second sock becomes right. There is no connection between them, but measuring the state of one sock by putting it on immediately determines the state of the other. Moreover, if we were to put this pair on our feet several billion light years apart, nothing would change. The second sock would still instantly become right, which intuitively violates the prohibition of Einstein's special theory of relativity to exceed the speed of light. Shock. If initially it was believed that quantum effects apply only to subatomic particles such as electron or photon, Then, with the development of science, scientists managed to enter the state of superposition, first atoms, then in 1996. The experiment was successfully conducted with fullerene molecules consisting of 60 carbon atoms. In 2011, a similar experiment, interference of organic molecules of 430 atoms. And in 2019, Marcus Arndt from the University of Vienna managed to achieve diffraction of molecules consisting of 2,000 atoms each. And it's quite possible that this can even be achieved with viruses. And that, if you've ever had an acute respiratory infection, is quite a tangible thing. But why is it so difficult? It's because in order to introduce an object into a superposition state, it must be completely isolated from the external environment. After all, even one particle having interacted with it will cause wave function collapse, or decoherence, as it will measure the state of this object by this interaction. Isolation, by the way, is achieved by placing the object in an absolute vacuum and cooling it to absolute zero, so that even thermal radiation does not destroy the superposition. You might have the mistaken impression that phenomena such as entanglement are incredibly rare and that we are only able to obtain it in a laboratory experiment. But that's not true. The vast majority of particles in the universe are in an entangled state. It arises every time particles collide and decay, the splitting of the light flux, in non-linear crystals, and so on. Moreover, even particles of our bodies are constantly entangled. Just this entanglement is almost instantly destroyed, because these particles are in almost continuous interaction with others. And in the case of quantum mechanics, not even a direct impact, but in general, any exchange of information causes decoherence. As Austrian physicist Anton Zeilinger writes in his article, experience shows that coherent quantum superposition is destroyed not because of uncontrolled, perturbing influence of macroscopic device on microscopic object, as it is claimed by many authors, but due to information exchange between subsystems. What is meant here is that measurement is not necessarily a direct physical contact, but primarily an exchange of information. And that is why, in the case of a detector on only one of the slits, the electron superposition breaks down. It's time to turn to the heavy artillery. The following experience can really shock you. It has a lot of variations, but we're going to look at the most interesting one, the two-slit Miller experiment with delayed selection. Once again, we have a photon source, again a screen with two slits, behind which is a nonlinear crystal of barium, beta borate, that turns one photon into two entangled photons. In this way, we can measure one photon without affecting the other. The first one goes to the lens, which collects all photons passing through it on the zero detector, thus seemingly erasing information about which of the slits it passed through. Another photon flies to the prism, directing it to translucent mirrors A and B, from which it is reflected with 50% probability and gets to detectors 1 and 2, or passes through them, collides with another translucent mirror, and gets to detectors 3 or 4. The result of each photon shot is registered by a coincidence counter connected to the detector. It turns out that if the photon hit detectors 1 and 2, we can tell exactly through which of the slits the original one flew, and we will see the classical distribution, 2 bands. And if the detectors are 3 and 4, then quantum erasure occurs, because again, it becomes unknown through which slit the original photon flew, and we will see a diffraction pattern. Have you already guessed what the shocking element is here? The fact is that the photon traveling to detector 0 reaches it 8 nanoseconds, faster than its entangled brother traveling to the other 4. Then, how does it know what pattern to show at detector 0 if its measurement or non-measurement has not yet occurred? How does he choose a pattern that depends on the behavior of the photon entangled with him in the future? Can we really influence the past with our measurement? It's no longer about the trees or the moon. Is this time travel? Unfortunately, or fortunately, in this case, everything is not as it seems at first sight. And there are several different explanations of this phenomenon at once, reflecting the main interpretations of quantum physics. One of them says that since photons move at the speed of light because they are light, time becomes relative for them. And if, for the observer, there is a difference in the time of their measurements, then for the entangled photons themselves, there is no difference, and these events are simultaneous for them. Another explanation, consistent with the so-called Copenhagen interpretation of quantum mechanics, tells us that when one photon hits detector 0, the wave function collapses. The photon has occupied a certain position, and the entanglement between photons is destroyed. And then, it is simple. If the first photon on detector 0 falls into the region of maximum of diffraction pattern on the hill, it means, most likely, that the initial photon before separation passed through both slits, and the probability of the second photon hitting the detectors is redistributed. Now it has a much better chance of hitting detectors 3 and 4. If the point is closer to the minimum in the depression, then most likely the original photon went through one slit, and the second photon is more likely to hit detectors 1 or 2. No problems with time travel, observer effects, and causality. Moreover, if we combine the patterns from detector 0 corresponding to detectors 3 and 4, this is when we don't know the exact slit. It turns out that the points on them don't coincide, and the diffraction pattern is replaced by the classical distribution. The MindWorld's interpretation states that each dimension of the state of the photon forms its own parallel universe, in one of which it passed through one slit and in another of which it passed through several. So there is no contradiction. We just happen to be on one branch or another. There can be as many such universes as you like, and there are innumerable of them being created every moment of time. There is also instrumentalism, described quite succinctly by David Merman. Shut up and calculate. As you can imagine, proposing to simply use quantum mechanics as a tool and not really question it. Existential, considering the whole universe as an observer, relational, wave pilot theory, objective reduction, quantum Bayesianism, and quantum Darwinism. There are quite many theories, and one is more extravagant than the other. The theory of superdeterminism, whose proponents claim that everything in the universe is predetermined before the Big Bang, and that there is no free will. But it is not possible to say with precision which of them is right, although attempts are being made. For example, Albert Einstein being an ardent opponent of the Copenhagen interpretation of Niels Bohr, in which the central place is occupied by the distribution of probabilities. Refuting this, utters the most famous phrase, "God does not play dice," arguing that quantum processes cannot be subject to chance. To which Niels Bohr issued the equally famous response, "Don't tell him what to do." Einstein then co-authored with Boris Podolsky and Nathan Rosen the so-called EPR paradox. Briefly, he proposed finding a way to measure both coordinate and momentum simultaneously in entangled particles, which contradicts Heisenberg's uncertainty principle, one of the basic tenets of the Copenhagen interpretation, which states that it is impossible to know both a particle's coordinate and momentum simultaneously with great precision. Instead, Einstein proposed the theory of hidden parameters. That is, the behavior of quantum particles is deterministic, predetermined in advance by some hidden parameters. And the collapse of the wave function does not violate the principles of local realism, but only exposes the result predetermined, not yet discovered characteristics. Sounds good. Plus, Einstein's authority equals a worthy opponent. But how do we know who is right? John Stuart Bell offered a solution when he derived an inequality that could resolve the dispute. Bell's inequality in classical physics always holds, and if the hidden parameter theory is valid, it should hold in quantum physics. The first experiments followed, in each of which this inequality was violated for entangled particles. Each such result became the subject of discussions, connected mainly with imperfection, chosen by scientists of accidents. For the purity of the experiment, we needed absolutely random values, which are actually quite difficult to obtain. After all, as we know, any exchange of information, even indirect, even through billions of interactions, destroys the superposition and affects the outcome of the experience. Apparently, the violation of Bell's inequalities in each of the experiments performed means that Einstein was wrong, and there are no hidden parameters. In 2020, on the basis of all the same experiments, appeared the so-called no-go theorem of the prohibition, according to which one of 3 principles is exactly violated in nature. If locality is violated, it means the possibility of instantaneous, faster-than-light-speed interaction between particles at any great distance, or so-called spooky long-range interaction. If realism is violated, then we cannot speak objectively about the certainty of the results of measurements that have not been made. That is, we cannot be certain that the moon exists without our attention. But if the existence of freedom of choice is violated, then here everything is again reduced to superdeterminism, and everything is predetermined with precision long before the appearance of mankind, and will be predetermined after its disappearance. Any of these principles is purely logically difficult to reject, and each interpretation of quantum mechanics rejects its own, which further divides the proponents of the different concepts. The subject of quantum physics is, frankly, a bottomless one. After all, it also doesn't give us an exact solid answer either. Is there a moon after all? And will there be the sound of falling wood where we are not? We cannot say with precision whether the materialists or idealists, the proponents of the Copenhagen, or the many worlds interpretation are right. We can only make a choice, and that only if we have free will. Moreover, we can be wrong in general, and our universe is a dream, a simulation, or it doesn't exist at all. But it is in such arguments that truth is ultimately born. So if I'm wrong somewhere, please correct me in the comments, and together we'll get a little closer to the truth. It is an amazing and beautiful thing. Science is. It seems that any simple reflection can eventually take us to the cutting edge of knowledge and leave us in the dark. It is literally riddled with paradoxes of all kinds. It is as if our brains themselves are not equipped to understand complex constructs such as quantum physics or philosophy, leaving us floundering in a powerless and fruitless search for an idea that can exhaustively explain everything. Science in general is a paradox in itself, for while it aims to provide answers, it mostly generates questions. We study, we make mistakes, we argue, but in the end, as I said, humanity has incredible potential. For now, I can only hope that when this video comes to an end, I will not disappear from your reality like the moon or the sound of a falling tree. I will continue to ask questions so that you will come back here one more time to see if this video really exists.